Good afternoon, everybody. Today is lecture number 6, and this lecture will be dedicated to the problem of thermodynamics of mixtures and chemical reactions. What is mixture? Well, if we look at the phase diagram of helium, as we discussed last lecture, then we can see that helium can be in 4 different phases: liquid phase, another liquid phase, gas phase, and solid phase. And looking at this phase diagram, you can ask yourself, can we realize a situation where not 3 but all 4 phases are in mutual equilibrium? So we have here a mixture at the triple points. We have a mixture of 3 phases, but is it possible to have a mixture of 4 phases? So the goal of my lecture, one of the goals of my lecture today, is to explain if it is possible or not. What is mixture? 2 or more materials or substances are mixed together but do not chemically combine, and the constituting substances retain their original properties and can be physically separated. In this case, we will call a substance a mixture. In order to talk about mixtures, it is convenient to introduce a new quantity, and this quantity is called chemical potential. Let me explain you what it means. Imagine we have a volume, and this volume we have a gas, and the 2 parts of this volume are separated by the wall, and then there is a valve here, and I have a possibility to open or close this valve. I do such that in one case, on one side, I have volume 1 and number of particles is n1. On another side, I have volume 2 and number of particles for the gas n2. And I know that under certain conditions, if I open the valve, particles will diffuse from one part of this volume to another part. And this phenomenon is called diffusion. So diffusion aims to equilibrate concentrations of particles. How to understand this diffusion thermodynamically? And this would be one of the first goals of this lecture, to understand diffusion thermodynamically, to develop physical theory of diffusion. In this case, I will again use Gibbs function as a thermodynamic potential. But since the number of particles now changes, I will write thermodynamic potential, a change of thermodynamic potential, as a change of number of particles on the left side times derivative of thermodynamic potential with respect to number of particles on the left side, and a change of thermodynamic potential due to the change of number of particles on the right side of this volume. Since total number of particles is conserved, and since I'm talking about thermodynamic equilibrium, these 2 expressions can be written, from where it follows the derivative of thermodynamic potential of the gas on the left with respect to number of particles on the gas on the left should be equal to the thermodynamic potential, to the derivative of thermodynamic potential of the gas on the right with respect to number of particles on the right side of this volume, if we talk about thermodynamic equilibrium. Well, looking at this expression, you can ask yourself, why don't we introduce a new variable and state that at thermodynamic equilibrium, we should observe equality of this variable. And that's exactly what people do. They introduce a new variable which is called chemical potential. Chemical potential is equal to derivative of specific Gibbs function with a number of particles while keeping temperature, or if you talk about situations with changed pressure, also pressure fixed. And as we can see, if you talk about diffusion, diffusion is about equilibration of chemical potentials. So in thermodynamic equilibrium, chemical potentials should be equilibrated. As an exercise, let's calculate chemical potential for the case of mixture of ideal gases. So we do this for a specific component of this ideal gas. So we'll call Ni is a number of moles of ideal gas I. Then we can introduce quantity which will describe concentration of this ith component of the ideal gas. And it would be then number of moles of this gas divided by total number of moles of the mixture of gases. And you can also see that concentration can be expressed in terms of ratio of pressures for the gases. Then, from the definition of the Gibbs function, and differential of this thermodynamic potential, you can see that Gibbs function for the ideal gas I is such that if you take its derivative with respect to volume, you will get, with respect to pressure, you will get volume of this gas. This is more or less the definition of the Gibbs function. And since for ideal gas we can write an expression like this, where R is a universal gas constant, T is the temperature, Pi is the pressure of this ith component of gas, and N is the concentration. Sorry, N is the number of moles. Then if you now take this expression and integrate this with respect to pressure, you'll obtain that Gibbs function as a function of pressure of the gas and temperature is equal to integration constant as a function of temperature plus number of moles, or T, and then logarithm Pi. using the fact that sum of partial pressures of gases will eventually give the total pressure of the gas of the mixture of these gases, then we can rewrite this expression slightly differently. And here you can notice that since number of particles of the gas is equal to number of moles of this gas times Avogadro constant, from this expression and from the fact that we are talking about ideal gas in which particles do not interact, so we can actually forget about mutual interactions and energy which is associated with these interactions. It means that total Gibbs function is equal to the sum of Gibbs functions of particles, and if we now want to calculate chemical potential for the case of this gas, it would be just specific Gibbs function, not specific one, but Gibbs function divided by number of particles, and it means that it would be equal to G temperature plus RT logarithm P plus RT logarithm I divided by Avogadro constant, and this eventually gives me part of the chemical potential that will depend on temperature and total pressure, plus a part that will depend on the concentration of the gas, where instead of constant R, I have new constant, which is called Boltzmann constant. As you know, this Boltzmann constant is universal gas constant divided by Avogadro constant. So this is expression for the chemical potential of ideal gas in a mixture of gases. Why do we need this chemical potential? How can we benefit from it? As you can see already from this expression, then the chemical potential is in fact Gibbs function of a single particle. So we can actually operate with a chemical potential as a Gibbs function. And we also concluded that we can define the equation, the condition for equilibrium, which eventually stops the diffusion process, as the condition of equality of chemical potentials. Another example where we can see the strength of the concept of chemical potential is a phase rule. Imagine I have a mixture of many components, and each of the components can be in many phases. I would like to understand how many phases of different components could be at equilibrium at the same time. For instance, if you come back to the original question that I showed at the very beginning, helium has 4 phases. I would like to answer question about number of phases that can be at equilibrium at the same time, maximum number of phases that can be at equilibrium at the same time. As I said, I will talk about chemical potential, and for each chemical potential I will also define 2 coefficients. One coefficient will show me the number of phase, and the second index, first index will show me the phase, and the second index will show me the component. So it means that, for instance, if you talk about component I, if I have thermodynamic equilibrium, that the second phase of this component is in thermodynamic equilibrium with the first phase of this component, and it means that the chemical potentials are mutually equal. And then for each of the components, I can write a number of equalities. And eventually, if I have R phases and C components, for each of the R phases and C components, I can write expressions, equalities, such that in total here, if you calculate how many equalities I can get, it would be C minus 1 times R. Equations in total. Sorry, it's different. R minus 1 times C. C components, C lines, and here I have R minus 1 equalities in one line. How many variables I have in this case? Well, in principle, every of chemical potentials for whatever phase we're talking about, and every component we're talking about, every of the chemical potentials will depend on concentration, as we could see in the example of ideal gas. How many independent concentrations we have in this case? Well, if we state that the total number of particles is fixed, then the concentration for kth phase and ith component will be calculated like this. And looking at this expression and stating that the total number of particles is fixed, you can conclude that in principle you have C minus 1 mutually independent concentrations in each phase. Basically, it means that if you take a specific phase and no concentrations of C minus 1 component, taking into account the fact that total number of particles is fixed, you can calculate the last concentration. So basically, it assumes that the total concentration for one component. For one phase, the total concentration is equal to 1. As a result, we have C minus 1 independent concentration for each phase. We have R phases, and it means we have C minus 1 times R independent variables while we talk about only about concentrations which define chemical potential. But also, in the case of ideal gas, we saw that chemical potential depends on pressure and temperature. So it means we have two more parameters. The total number of variables we have here in this case is C minus 1 plus times R plus 2. So let's summarize what we have here. We have R minus 1 times C equations, and they have C minus 1 times R plus 2 variables. And obviously, if you want that the system of equations has at least one solution, we must have more variables than equations, or at least equal number of variables than equations. So it should be inequality like this. Otherwise, number of equations is more than number of variables, and such a system doesn't have a solution. And let's look what it actually means. RC minus C should be less or equal to RC minus R plus 2. Then R and what we observe, we obtain an equality that says that number of phases that can be at equilibrium at the same time is equal or less number of components plus 2. So if you have just one component, C is equal to 1, and the number of phases that you can get at thermodynamic equilibrium at the same time is either equal to 3 or less than 3. And this is exactly what we saw in phase diagram. If you look at the phase diagram of helium, we could find triple point where 3 phases coexist, but we never saw a point at which 4 phases would coexist. This is stated by this rule. This observation is confirmed by this rule, which is called phase rule or Gibbs rule. And there is also another formulation of this rule, which explains the very same thing, but in terms of number of independent variables. Look at the phase diagram of helium, for instance. If we have just a gas, we can change pressure and temperature independently. We have 2 degrees of freedom. If we have an equilibrium of gas and liquid phase, we can change either pressure or temperature independently, and the rest should be tuned to maintain thermodynamic equilibrium between these 2 phases. We have 1 degree of freedom. And looking at this trend, you can conclude that if you have a triple point is unique. You cannot change pressure, or you cannot change temperature without losing equilibrium between 3 phases. So it means we have 0 degrees of freedom. Therefore, the very same rule can be formulated in terms of degrees of freedom. Degrees of freedom, and this is written as 2 plus C minus R. So if you have C number of phases and so if you have C number of components and R number of phases, the total number of degrees of freedom is 2 plus C minus R. And as I said, this is the very same rule as written here, just formulated quite slightly differently. The total number of phases that can be at equilibrium at the same time is no more than number of components plus 2. This rule, as I said, is called phase rule, or sometimes it's called Gibbs rule, and it was suggested by Gibbs. You can see the copy of original paper from 19th century in which this rule was formulated. And the final example that shows the importance of the concept of chemical potential is the example of chemical reactions. So here I have a pictorial demonstration of chemical reaction where I have initially have mixture of two types of atoms, and as a result of chemical reactions we have a new compound which is built out of these two types of atoms. I will go through these slides without showing derivations on the blackboard, because these are very simple derivations but rather lengthy ones. And in order to discuss this, I take an example of so-called reversible chemical reaction. The reaction can go both ways, directly from left to right or inversely from right to left. And when the speeds of the direct and inverse reactions are the same, the chemical equilibrium is reached and the masses of the participants of the reaction do not change anymore. The reaction effectively stops. So I take an example of the reaction shown on this slide. I write the expression for chemical reaction slightly different. It's not a chemical expression, it's more mathematical expression now, showing that I have a number of participants in the reaction, those that are consumed if we talk about direct reaction, and those that are produced. And I will write this, as I said, I will write this reaction in a mathematical way where J large would correspond to the compound, and nu, the coefficient in front, will correspond to the coefficient in front of compounds, and it would be negative if this is substance which is consumed during the reaction, and positive if it is produced during the reaction. Then we write thermodynamic potential in terms of chemical potential. Remember that chemical potential is basically Gibbs function for a single particle. Then we take into account that at thermodynamic equilibrium, thermodynamic potential doesn't change, and it means that if you write the sum of all these coefficients of all the products of the coefficients nu and chemical potentials, then we will have 0 as a result, and this it will eventually give me equation of reaction equilibrium. So here we have an equation that describes equilibrium of the reaction. Then we repeat few simple steps, the very same steps we did in the derivation of chemical potential for ideal gas. So basically take an assumption that participants and the compounds which are produced all the participants compounds which are produced during the reaction, compounds which are consumed during the reaction, they satisfy the physics of ideal gas. And we rewrite this expression of equilibrium in the chemical reaction in a slightly different form, taking into account the expression for chemical potential of ideal gas. Then, as I said, we make several steps which are simple steps but take quite some space. If I do this on the blackboard, and you will see that if you look at the product of concentrations of the participants in the reaction, it would be equal to some constant K, which will be function of temperature and pressure. So the ratio of the powers of concentrations of the reactants entering the reaction and reactants produced during the reaction is a constant if the temperature and pressure are constant. Well, this is something that you have seen before. If you remember at high school and the course of chemistry, you use such a thing as Evenwichtkonstante, so to say equilibrium constant of chemical reaction. With this expression, you can see the physics behind this constant. And the physics behind this constant is called law of mass action. The law of mass action was discovered again in the 19th century, and you can see here the two papers which claimed mutually independent discovery of this law. Not everything is described in chemistry with the help of thermodynamics. In 20th century already, Boris Belousov discovered a chemical reaction that showed oscillations. So instead of development of chemical reaction towards equilibrium, when you mix two compounds, then they enter the reaction and eventually reach thermodynamic equilibrium in a similar way as if you start diffusion of two compounds, and then eventually, due to diffusion, these compounds equilibrate the chemical potentials and then reach thermodynamic equilibrium. In the case of Belousov, he succeeded to realize the situation when actually reaction oscillates. And in order to show that it was absolutely unexpected, just in the middle of 20th century, that I would like to mention that the article where Belousov tried to describe his findings was not published for about 7 years. It was rejected from all scientific journals with the statement that it is theoretically impossible. So something which was discovered in the lab was believed to be theoretically impossible. And only afterwards people succeeded to explain this, and it was the people realized that the reaction indeed proceeds via oscillations, and it was more a predator-prey society model when if you have, for instance, a number of rabbits in society, number of wolves, and if you look at the population of rabbits and wolves in the society, it will oscillate in time, in out of phase. And something like this also happens in the case of Belousov-Zhabotinsky reaction, so that the simple thermodynamic theory of chemical reactions that I just demonstrated to you is not completely true. Mixing four solutions will launch a reversible chemical reaction. Intuitively, one can predict that the reaction will reach a thermodynamic equilibrium and stop in accordance with the law of mass action. We see that the solution is first blue, afterwards it becomes green, and eventually it acquires a red color. However, the reaction doesn't stop, it goes on. The solution becomes green and blue again, and afterwards green and red again. The solution changes its color with a well-defined period in time. A reaction like this was discovered in 1951 by Boris Belousov. He tried to publish these findings, but his papers were rejected. It was believed that oscillating chemical reactions are theoretically impossible. He eventually published the data 8 years later. The mathematical model which explained the results was proposed by Anatoly Zhabotinsky in 1964. In literature, the reaction is called the Belousov-Zhabotinsky reaction. The mathematical model which explained the results was proposed by Anatoly Zhabotinsky in 1964. In literature, the reaction is called now the Belousov-Zhabotinsky reaction. So we reached the conclusions of the lecture today. The concept of chemical potential certainly enriches thermodynamics and allows to account for diffusion. We derived Gibbs rule that describes equilibrium between several phases, and physics of mixtures and chemical reactions can be described using concept of chemical potential. Thank you very much.